Here we go with the second part of our additional aspects of equilibrium. In this section, we're going to talk more about solubility and when precipitates form and things like that. So solubility products. So we had an equilibrium that exists in a saturated solution of barium sulfate and water. So barium sulfate being a solid, something we haven't really worked a whole lot with, that's also going to dissociate into barium ion and your sulfate ion. The equilibrium expression for this, because it's a solid and we don't really care about that as far as that's concerned, would just be the concentration of the two ions, the aqueous ions. And we're specifically, in this case, we call this the solubility product. So KSP is called the solubility product. Obviously, it's the same thing as the K was that we've been dealing with all along, just like Ka is the same as the K we've been dealing with all along, just a different subset. KSP is not the same as solubility, though. Solubility is generally expressed in the amount that can get dissolved. So the mass of solute dissolved in 1 liter, so in grams per liter or grams per mil of a solution, or sometimes we talk about the molar solubility, so moles per liter, the molarity. And using this flow chart here, you can kind of go different ways depending on what you have. So if you know the KSP of a solution, you can use the equilibrium to figure out the molar concentrations, and once you have the molar concentrations, you can get the molar solubility, and then from there, it's just you have the formula weight and converting moles to grams like you did way back at the beginning of the year, and you get the mass solubility. Or if you had that, then you can go this way and get the KSP. So you can go either way through that little flow chart to get what you need, depending on what you're given to start with. So let's try an example of this. The KSP for calcium fluoride is 3.9 times 10 to the minus 11 at 25 degrees C. So assuming that it dissociates completely and nothing else is really going on, what is the solubility of calcium fluoride in grams per liter? So that's the little bit harder one to calculate, in grams per liter. So how do we do this? So you can use that KSP expression to get the equilibrium concentrations, and then we can calculate the solubility, and then from there we can get mass solubility. So just like we saw in that chart over there. So to get this, we're going to do our ice chart. We're not going to worry about this over here because this is a solid. And so when you first start off, you have none of this, and this is going to change by x. And for our balanced equation, this is going to be 2f because you have F2, so this is going to change by 2x molar. And so KSP equals these two concentrations. That's your equilibrium expression. We're going to plug in our x's. So KSP equals 4x cubed. We have our KSP set it equal to 4x cubed. And so x equals the cube root of 3.9 divided by 4. 2.1 times 10 to the minus 4. So our x is 2.1 times 10 to the minus 4 molar. So the molar solubility of calcium fluoride is 2.1 times 10 to the minus 4. So calcium is 2.1 times 10 to the minus 4, and it's a 1-to-1 relationship with calcium fluoride. 1 to 1. So this concentration of this ion equals concentration of this altogether. So 2.1 times 10 to the minus 4 moles per liter. But they asked us to calculate the mass solubility. So we know 2.1 moles of calcium fluoride per liter, and just convert that to grams basically. 78.1 grams per mole is 1.6 times 10 to the minus 2 grams of calcium fluoride per liter of solution, and that's your molar solubility. So we talked about the common ion effect at the beginning of the last set of notes. This is obviously going to affect solubility as well, right? We talked about that affecting how much of a chemical would dissociate, kind of the same idea. So if you have some of the ions in the solution equilibrium that's already dissolved in that solution, that's going to again shift back to the left to try to consume that, and so the solubility of the salt will decrease. So still working with the same reaction here, you get your barium sulfate going to barium and sulfate ions. Imagine we're going to calculate the molar solubility of calcium fluoride at 25 degrees, and the solution is 0.01 molar in calcium nitrate. The KSP for calcium fluoride is 3.9 times 10 to the minus 11 at this temperature. So this is basically the same problem we just did, but now there's some calcium nitrate in the solution, and we're going to compare this solubility to the solubility that we got in the previous example. So it's solved just like a standard equilibrium, except we're also going to have an initial concentration in our products. So again, looks just like our other one. The nitrate is a spectator ion. We don't care about that. But instead of a 0 here, we have 0.01 molar. So that's the ion we care about. And so we're still going to add some unknown molarity. We're going to add twice that much because there's a 2 here, 2x molar, and this is 0.1 plus x molar. So we still have that same equilibrium expression, 0.01 plus x times 2x squared. But again, we have a very small KSP. We've been making this assumption all along. We can assume that x is very small compared to 0.01. If you don't believe me, just look at what x was in our last example, 0.00021. Rules of sig figs. If you add that, you're still going to get 0.010. So we can assume that x is negligible, which makes our lives a little bit easier. And so 3.9 times 10 to the minus 11 equals 0.01 times 2x squared. Solve for x. And so x is 3.1 times 10 to the minus 5th molar. So the molar solubility of calcium fluoride with that common ion is 3.1 times 10 to the minus 5. Well, the same, right? Again, same principle, same. That's the concentration of calcium, which is also the concentration of calcium fluoride. As expected, this number is smaller than the 2.1 times 10 to the minus 4 molar we got without the common ion in the first example we showed you. So some things that can affect solubility of solutions other than the common ion. The pH can affect the solubility of something. So if the substance has a basic anion, it will be more soluble in an acidic solution, and the reverse is true. If it's got an acidic cation, it's going to be more soluble in a basic solution. So when they ask you about when things are basic, you'll want to be looking at those. And so, for example, which of the following is more soluble in an acidic solution than a basic solution? Barium fluoride or silver chloride? So what do you have to do to figure this out? Well, you have to think about your the ions that you're making. Fluoride, if that were with an acid, would be HF, and you have to ask yourself, is HF a strong or a weak acid? HF is a weak acid, and conjugate bases of weak acids are basic. And then silver chloride, chlorine ion, is the conjugate base of hydrochloric acid. That's a strong acid, so its acidity is negligible. So in this case, barium fluoride is going to produce the F, which is basic, so that'll be more soluble in the acidic solution. And like I said, Cl, basically nothing, and so it's going to be unaffected by the pH. Other factors that can affect solubility are complex ions. So metal ions can act like Lewis acids and form complex ions with Lewis bases in solvents. These are some examples of some of these complex metal ions. Basically, if you've it's unlikely you would see something like this, or at least less likely. But if you recognize some of these, just keep your eye out for these metals. They'd like to ask you about this one a lot. Silver ammonium ion complex. If you see these heavy metals and things like that, then maybe that can set off some warning bells in your brain. So the way that works is, imagine you've got your silver chloride just kind of chilling here at the bottom of this, and if you were to add some base, a weak base NH3, that's going to react with the silver to form that metal ion complex, the AgNH3-2. And once you do that, now you've removed some of the silver from the solution, which is going to allow the equilibrium to shift sort of back. We're going to shift it towards the right because you've freed some of that up, and so it's going to increase the solubility of that silver chloride. So if you added enough, you could actually get this to totally dissolve. Amphoterism, so amphoteric metal oxides and hydroxides are soluble in strong acids or bases because they can act as either acids or bases. Unlikely to see something like this, really. But some of these cations that you might have to keep your eye out for: aluminum and zinc and tin. Another thing you will probably see is, will a precipitate form? And so we can bring back our idea of Q, which is the same thing as the equilibrium expression except with non-equilibrium amounts. And so if Q is equal to KSP, the system's at equilibrium and the solution is totally saturated. If Q is less than K, that means we got to make Q bigger. So you're going to be able to dissolve more solid can dissolve because we're going to shift that equilibrium to the right to get the K EQ to equal KSP. And then if Q is greater than K, the salt is going to precipitate out until you get back until it's equal. And you can use that, you can use those differences in solubility to like separate ions in a mixture. So this is just a big sort of like flow chart of an example of how you could do lots of different things to get different ions to come out of a mixture of lots of different stuff. Unlikely to see anything like that, but something highly likely you will see is asking, will a precipitate form, or even maybe a little bit more complicated is which one is going to form first, which is what an example like this is. So you've got a solution that contains 0.01 molar silver ion and 0.02 molar lead-2 ion. And when chloride ion is added, you could make AgCl with this KSP and lead-Cl, lead-2 chloride, with this KSP. And so the question is here is what concentration of chloride ion is required to begin the precipitation of each salt, and then which salt will precipitate first. So to do this, we can just use your KSP expression and solve for Cl minus. And so that's going to tell you the amount at equilibrium. So since you're at equilibrium, if you were to add any additional Cl ion, that's going to cause some precipitation because now you've shifted your reaction, you're shifting it back to the left to cause that extra to get used up. So if we're looking at AgCl, here's the reaction we're looking at. AgCl is going to dissociate into Ag plus and Cl minus. So your equilibrium expression would be this right here. You have your KSP for AgCl, and you add this to start off with. So we're going to solve for chloride. And chloride is 1.8 times 10 to the minus 8 molar. So that's how much it would take to be saturated, to be at equilibrium. Similarly, for lead chloride is going to dissociate into lead ion and 2 chloride ions. And so your expression should be a little bit different because the Cl is going to be squared, but same principle still applies. You're going to take the KSP they gave you and set it equal to your equilibrium expression, plug in what you have. This is your unknown Cl minus. Solve for Cl minus is 2.9 times 10 to the minus 2 molar. So that's the amounts that it's going to take for those solids to start to precipitate. And which one's going to precipitate first? The AgCl is going to precipitate first because it requires a smaller concentration. So if you're adding chloride ion, you're going to get here first. So you're going to start to get AgCl precipitating before you start to get lead chloride. And that is it for this unit.